hear me well online. I'm very pleased to be giving this talk here at ATH about the research component of our twinning project, which is called AIoT Twin, which is about artificial intelligence of things, because I work in the domain of Internet of Things for at least 10 years now. And with the advent and development of AI, actually, we are bringing AI and more intelligence into the physical world, which opens up new possibilities, opportunities, but also new challenges for us as the technical people. So I will be talking about recent research results of this project AIoT Twin. But first, let me introduce briefly the university from which I come from, which is the University of Zagreb, which is the biggest Croatian university and the oldest in this part of Europe. It was founded in 1669 already, and it covers a really large number of disciplines. And my faculty is one of the constituents of the University of Zagreb, where we have programs both on electrical engineering and computer science, with 3,500 bachelor and master students altogether, around 500 postgraduate students, and around 300 academic staff. And in particularly, I work within the IoT lab, which is part of the Department of Telecommunications, which is then one of the departments of the faculty. And just let me say that we are a small group. Altogether, we are 10 people who are working also on this project AIoT Twin, with 3 faculty members, my colleagues, Gordon Ježić and Mario Pušak. I head the lab currently, and we have currently 7 students. We had some also postdocs, but unfortunately they decided to go to the industry as life changes over time. I just wanted to introduce what we do within the lab. We've been doing research in the area of IoT for now more than 10 years. So the lab was established in 2015. And we have been doing a number of projects in this domain. The first 3 projects on this list are funded through the European funds, through Horizon Europe, this last one. Then this one was Age 2020 project on interoperability within the IoT domain. And we started also with the Open IoT project back then in 2013, and this was just one of the first projects on actually on semantic cloud-based IoT solutions. Currently, also we have a new project that you can see, which is Digify, where we are going to work also on XR communications integrated with IoT and the physical world. And this is also an interesting project because the Ericsson Nikola Tesla company, which is based in Zagreb, is a partner in this project. And then we were using IoT also in the fields of agriculture and smart spaces like smart homes, smart offices, and so on. Yeah, the last one is just the industrial project, which is running for quite
recording in progress.
I'm so sorry.
Yes, yeah, he was born in Croatia.
So sorry, Ivana.
No
I wanted to join the people online just in case they had questions. Please continue.
Yeah, I just wanted to mention the last project, which is the industrial project, which shows this continuation of collaboration on the topics with respect to machine communication, as it was called, back then in 2011. And now IoT with Ericsson. Let me now jump into the details of the AI Twin project. So this is a specific research project which is within the widening program. And it started in January 2023. And within the project, we are trying to, create new results. And we are striving for research excellence, as the European Commission says in the announcement of our project. So this is a coordination and support action, but still it has a research component, which is a very good thing for us. The consortium consists of 4 partners altogether. So University of Zagreb is the coordinator of the project, and then we have 3 partners. One of the list is RISE, as you have seen, and you have heard Sharuna Senseifa representing the RISE project here, at least physically. Then we have Technical University of Vienna also participating in the project, and Technical University of Berlin. So the strategic goal of the project is really to improve the scientific excellence and innovation capacity of University of Zagreb, because such twinning projects are designed in a way to focus also not only on the research capabilities, but also on the skills of a research group of PhD students and so on. And we are trying to create a stimulating research environment at the university to attract new national and international talents. This Videra program is specifically targeting countries which have a lower participation within the Horizon Europe program. But the good thing is that it involves now a research component, which is different compared to previous projects in such calls, that within this research component, we are developing this specific orchestration middleware for artificial intelligence of things, and this is what I'm going to present during my talk. So we come to the talk outline. Let me introduce what I'm going to talk to you about today. First, I will introduce the topic of AIoT, and then also orchestration at the edge. What does it mean? And why do we need specific orchestration middleware which deals with AI and IoT? So we have been working both on the learning part and on the inference part within this middleware, and I will be presenting our results, current results that we have produced so far, and then conclude with the future work. This is a photo from the last summer school, which was organized in Šibenik in Croatia last year. And this year we are organizing another summer school, the second summer school, which is happening in Dubrovnik. So you still have some time. There are some free spaces, places left for you to join if you would like now in the middle of September, the second edition of our summer school. Okay. Let's talk about artificial intelligence of things, what it is. Well, it comes from the IoT. I come from the IoT domain, not from the AI domain. So I bring this background with me. And I wanted to tell you what's the state of the art, in IoT. The number of IoT devices worldwide currently in 2003 that Statista reports is around 18 billion, and the prediction for 2030 is around 30 billion devices. Currently on the market, we have cloud-based platforms which are still predominantly being used by the big players, more or less. We have also a set of mature protocols which are used within the IoT domain, both at the wireless level and at the application level. That we can say is a kind of a solved thing, but we still miss some kind of interoperable ecosystems which can share data, share information across domains, and that we integrate, various things which are managed and governed by different IoT platforms. That is the problem of interoperability. But existing infrastructure, in a way, is underutilized because it would be more utilized if we would be able to share this information coming from various things deployed across various smart spaces. And users are really faced with a multitude of different applications tailored for their specific needs, for their specific infrastructure, but in a kind of silo way. That is the rule of the game still today. And people are always talking about smart something with respect to IoT, smart agriculture, smart cities, smart this and smart that. In my view, the current situation is such that we are not so smart yet, that we lack more of the processing capabilities and the smartness, that we are basically integrating things, putting them together, and we are able to interact with them, and we are letting our users interact and operate the things remotely from all over the world. But this is basically communication. This is not intelligence at the moment. So the Web of Things idea would be that we have a simple vision where we have devices being deployed that can simply interact with each other, and in this nice place we would have processing running on different devices which can trigger certain events. From, for example, here on the left-hand side, one device would send a sense command or an actuate command to another device that sends back reading to it, and then some interaction happens, something smart happens, and we are happy with the things being automated. But in reality, this is what we have. On the right-hand side that's the rule of the game, the state of the art. We have usually platforms which are deployed within the cloud. Then a user uses a mobile or a web app to interact actually with the platform core, where at this level of the platform core, we have virtual entities representing actual devices. So basically, the interaction happens to a virtual device here sitting at the cloud somewhere, and we have devices, either native IP devices that can directly talk to the core, or through a gateway that is more powerful, which then shields also these non-native IP devices beneath it. And so this environment is actually, in reality, when you would like to model it, it becomes a distributed environment with many processes running on different types of hardware, with different types also links, because different communication technologies are used at these links for communication and the exchange of information between the devices. So that's the reality which we face now, and basically all the smartness is put here into the cloud, where all this data comes, and then you do some kind of processing, you do the learning here in the cloud, and so it is all very, very centralized. But we would like to make it more decentralized, because I come from the world of distributed systems, where we would like to do things in a distributed and decentralized way. And also artificial intelligence of things is something that I see as the next evolutionary step of this IoT environment, where we want to bring AI actually into the smart and physical spaces, which is a little bit different from generative AI and completely digital space, because here we are actually combining digital with physical. Since then, here the boundaries between physical and digital world disappear, because we are going to operate some machinery in factories or in campuses, this smart physical spaces generate large amounts of streaming data continuously. This is the first part of this integrative story. So you have IoT devices that do sensing of the environment, that generate the data. This data can be used for the learning part, and obviously also for the creation of new models. Then we also need these new models for some kind of decision-making. The decision-making step is crucial so that you can decide what to do some acting, that you provide an actuation order to the machinery, to a smart bulb, that it lights itself with a certain color. And so really this actuation enables the physical space to become in a way alive and to react to, not only to events, but also to information and through the knowledge which is acquired through the learning and decision-making process. So then this physical environment really becomes, in a way, smarter, I would say. So let me give you an example of an IoT application, but really the simplest one that you can imagine. For me, this is the simplest example which shows how IoT actually can be combined with AI in a simple environment. By the way, this is something that also our students built as a small project at the bachelor lab. You can do like occupancy detection and smart lighting. So for example, what is the task of this solution is the following, that you have like Raspberry Pi. This is this edge node, like a device which doesn't have too much, resources. And this Raspberry Pi hosts an IoT platform. For example, it's Home Assistant, which is very handy for operating smart home environments, for the different types of smart home environments, devices. And we connect it to a smart light bulb, for example, Philips Hue. Not that I would like to recommend it, but okay. So through a gateway, it's connected to a smart light bulb, and it can adjust the color and brightness. This platform can adjust it based on the sensing part of our environment, where the sensing part comes from a video stream, because here I also host an ML model which can, count the number of people that are present in the room. And based on this, the ML model takes in the video stream coming from the camera, analyzes the number of people. This number of people is then sensing information for the IoT platform, and based on this, I can adjust the color and brightness on the lamp, and everything runs actually on one very small edge node. So why is it AIoT? Because I'm using an existing model. This is the inference part here that I'm using. I'm not here in this story. I don't have the learning part because the model needs to be prepared previously, and it needs to be also such that it is small enough to fit it onto the edge device where you have to deploy it. And then it becomes a source of information, the smart part of the information for the IoT platform, that it is operated autonomously. And then based on it, we provide decision-making rules here within the platform to change the color of the lamp. This is also all very, very simple. Now we're moving from the cloud to the edge. Now we are at the edge. But what happens if you would like to build a company that is providing such solution, all over Europe? You need a way to operate and install the platform on various edge devices. You need to operate all these components. You need to upgrade the IoT platform, and then things come kind of serious and interesting. This is a nice toy project for a group of students, but to build like an ecosystem of such solutions where this becomes a product where you can hook on different types of smart home devices to this IoT platform, where you can also manage the deployment of the software, where you can manage also the deployment of machine learning algorithms being deployed there, where you can build new machine learning algorithms based on the data which comes from these devices. Then this becomes really, really, really complex. And for this complex environment, we need this edge-to-cloud environment. That's the reason why from this simple example, we go to a more complex solutions that are really large-scale distributed systems. So in terms of challenges, we have a number of them. I have listed them here. So these are really, the problem is that we have a distributed and heterogeneous environments that have limited resources compared to the cloud. And our solutions therefore need to be accommodated to the resources which are at hand. Also, we have real-time data processing, so the data comes all the time from IoT devices. So you need to use ML algorithms which are adapted to online learning. And also, you have to take into account privacy and security requirements in the physical environment, where it is more critical than when you're in the digital realm. And to deal with this, we definitely need orchestration mechanisms and orchestration at the edge, because now we are in a completely new environment, which is not now only within the cloud where we have an abundance of resources, but in this environment, we are trying to push some of the processing tasks from the cloud closer to the edge devices and to the IoT. So in this environment, we are then talking about IoT edge-to-cloud continuum, which consists of different tiers. Here we have at the bottom IoT devices, then we have the edge layer, which is also divided here according to the devices. Now, the European Commission is happy with the terms far edge or near edge. Sometimes this near edge, which are more powerful devices closer to the cloud, they are called also fog layer. Fog layer would be this one, where you have more powerful devices, and the edge nodes, which are at the far edge, are like some gateways that are close to IoT devices, generating data continuously as time series data can span from the devices to the first hop node. If it does not, which can do some kind of processing, you can clean raw data from, for example, here, do some aggregation, some simple processing, and then you go up to this edge node, which has more processing power that can do some kind of learning already here. Or an inference model could be placed here. And then you can also join data stream coming from different environments at this layer. So the characteristics of this environment is that this is a multi-tier hierarchical infrastructure, which is heterogeneous. And one important thing is also that it is dynamic, which means this node can exit at any point of time. So it's like in peer-to-peer systems, nodes join and leave, they fail. Although it is hierarchical, because you still have the cloud resources which are residing and services which are residing here in the cloud. Yeah, so that in this environment, we need to do some orchestration. So here are the benefits and drawbacks of the IoT edge-to-cloud continuum. So what it offers to the AIoT domain: reduced processing latency, and it can also reduce the overall network traffic to the cloud. We're not sending raw data anymore to the cloud, but we are pre-processing it on the way. It can also offer improved reactivity because actuation decisions will happen earlier, closer at the devices which are one hop, for example, away from an IoT node. It also has increased scalability, resilience to failance, improved privacy and security is also what it offers, because the data does not need to leave a local network to go somewhere to the cloud. In this way, also, we have reduced operating costs. We're not paying so much to the cloud companies, but then we need to increase some capital costs and to push some money on the edge infrastructure. But then this environment becomes also increasingly complex. And we have unstable nodes with limited resources. And also we could have frequent and network changes, because in IoT domain, we have different, wireless technologies being used, which are also bandwidth limited. In such an environment, we would need orchestration, as we have orchestration in the cloud with Kubernetes, the well-known tool for orchestration within the cloud. Here at the edge, orchestration is a little bit different because here we need to manage the edge devices, which are heterogeneous, and we place services to these edge devices which are available. So service orchestration for the edge needs also to schedule, deploy, and manage these various services in this new environment, but also try to ensure that the required quality of service level are met based on the requirements of an IoT device or a specific application. Because, for example, when you are in the autonomous vehicle, in the domain of autonomous vehicles, you have to have reactivity within certain boundaries. Here on the right-hand side, you can see which are the functionalities such an orchestrator needs to implement. They are related to devices because it needs to have the registry of devices which are hooked within the system. It needs to know which are nodes. These are edge nodes that are available for the deployment of the services. The service registry is used for the services which you are deploying. You need to know also which algorithms you are using for scheduling those services, for managing them, and sometimes you need to migrate services from one edge to the other. And yeah, these are the essential building blocks then of this edge orchestration architecture. So remember that here, edge orchestration is general, so it does not focus specifically on services which are AI related. In technical terms, the orchestrators today are the managers of this whole infrastructure, and they are today deployed usually within the cloud. And this environment, the orchestration tools which are available today are such that they are centralized. What we did also within one study was to investigate how different orchestration tools available today, how they behave. We were doing experiments with Kubernetes K3s, which is the lightweight version of Kubernetes. By the way, this study is reported in the listed paper. Then we also investigated the performance of Kube Edge and IO Fog. And it turned out actually that Kubernetes and K3s had in the altogether the best performance in terms of startup time, migration time for the services, some overhead in terms of startup time, and also migration. Time overhead was the lowest. So the K3s is the lightweight version of Kubernetes. So it's really a stripped down version, which also allows devices from local networks to connect to an orchestrator which is within another network. That's why currently within our research we use K3s and Kubernetes altogether. We were also surprised that the memory footprint of both Kubernetes and K3s was kind of similar in a way. And now let's move on to orchestration middleware for AIoT. So what's so special about it? So what's special about it is that the services are now related to AI, that we have the learning part, that we are building new models, and that we have the inference part, and that we have to manage now these specific types of services. Each of these services also has some properties which are relevant for ML, for machine learning. Now we need to decide where will the inference service be placed, whether a specific model fits the device which is here at hand. We need to also decide whether we are going to do some federated learning scenario where we have aggregation of models coming from clients. So now this environment now needs to orchestrate such specific services which have different requirements. And that's why the orchestration middleware that we have, like the existing Kubernetes or K3s, is insufficient for managing and orchestrating such AIoT environments. That's what we did. also then to analyze what are the additional features which such environment needs to provide to us, so that we have an orchestration environment which is capable of operating AIoT services. So in this slide, you can see the requirement list. The ones which are black are this general purpose orchestrator tools, the features which the general purpose orchestrator tool offers to efficiently manage, monitor resources within the edge environment. That's what K3S can do for you. Collect information about the underlying network, deploy and manage these services within the continuum. But then these are then specific either for the learning pipeline, or they are specific for the inference part. We, for example, need to monitor the accuracy of an inferring service, and then to see whether we need to do something. We need to dynamically adapt to changes also in the system with respect to this inference performance. So these additional features is something that we are bringing into the orchestrator architecture, and that is what we did first by defining the general architecture based on the existing architecture of the general purpose orchestrators. So here in this slide, you can see our vision or our components that we have actually built, and we are still building and working on them, where we extend the existing orchestrators, which are, so these existing components are marked with yellowish rectangulars. They are the existing within the existing tools within Kubernetes and K3S. And we are adding these specific services which are needed at the node level. This is the edge node, which needs to be extended with services for the learning pipeline and with services for inference. And then on the orchestration part, we also need to do and integrate additional components also for the learning part and for the inference part. And yeah, this is what we are actually building within our project. Within the project, we're also focusing on the learning for federated learning, so that we support federated learning pipelines, so that these services, for example, here you can see how the general architecture looks when it does federated learning, because you have clients here on the far edge, which are nodes which are deploying these components for the learning part, and here at the near edge you have another component which does the aggregation of models coming from the clients in the lower end. And here at the orchestration level, we also have a controller for federated learning, which uses specific algorithms to define federated learning configuration, which decides how to deploy services for the learning part and for the aggregation across the edge environment. I will be telling you about it a little bit more with details in the following. This is one part of the game, the learning part of the game. Then we have the other part of the game, which is the inference part, where for the inference part, we would like to do the following. When a client or an IoT device sends data, it does not need to know where it's going to end up. It needs to end up at an inference service, which is adequate for, chewing and processing this data which comes from a device. And here we have extended Kubernetes with a proxy service so that we can send the data to the appropriate inference service, taking into account specific QoS requirements, which will also take into account the fact that, for example, this node disappears, and then the data will end up in, for example, at this inference service, because it also meets the QoS requirements. it is within the same domain, so that the security requirements are okay, and so on. So there is no need for the device to be smart, knowing where to send the data, but the environment is going to take care of it. This is also what we did with the inference part. So I will be talking still about the details of these two solutions, about federated learning and about inference. So let me just jump first to the hierarchical federated learning. So I was telling you that we do federated learning, but it's not the classical federated learning where you have just a client and one aggregator, but we have decided to go into the direction of hierarchical federated learning with local aggregators standing in between the global aggregator who is within the cloud and client devices, which are then at the bottom. So the reason for this is that this is a kind of also proposed solution to deal with the problem of communication costs which federated learning faces. Because in federated learning, you probably know, you have to ship models from the clients to the cloud, which can be far away, and those models can also be quite heavyweight. Hierarchical federated learning is proposed as a solution to this, and it fits naturally also this architecture of IoT edge-to-cloud organization, since you can use local aggregators within local domains, within local networks, to do the aggregations, within the same network domain, and then ship already aggregated models to the global aggregator who is sitting in the clouds. I mean, there are many challenges also with this hierarchical federated learning, as we learned through the work on this topic, because you have also unbalanced data distributions. And there is a question, how will you organize also the clients to form these clusters, because clients have different data distributions, which then affect also the performance of the learning pipeline. Yeah, so there are pretty much a lot of challenges with respect to this question, and this is I have to say that this is the ongoing work we are doing with a group from Technical University of Vienna, with Professor Sharam Duzdal on the problem of hierarchical federated learning. So, for example, this is just so what the group in Vienna was doing is that they have extended the Flower framework in such a way that it can support this hierarchical federated learning, and it works in a way that you define epochs, which are the local, clients. So they train the models for the defined number of epochs, and then after they finish this training round, then you have the local rounds for also getting the models being shipped from the clients then to the local aggregators. Then they aggregate the model here at this level, and then after 4 local rounds are done within the aggregator, you have a global aggregation happening within the cloud, and then this global model is shipped back to the clients. And this can also create certain communication costs. But now the communication costs is different when you send everything from the client just to one aggregator. So the communication costs is something that we want to optimize, and also there is a question, how can we put and organize these clients into clusters? So what happens then when new node comes in? There is a need maybe for a reconfiguration. You don't know where we will put the new client. What is the distribution this client is bringing in. So this is something that we are playing around with. There were many also experiments being done, but I will not go into too many details because it's also the question, how will you distribute? So what happens if you have different data distributions between the clients? On this right-hand side, you have a situation where each client has just a portion of the data set. And in this one, on the left-hand side, is an extreme situation where you have just one class of the data set per client. So situation is different, as I say. It's not so easy to decide what will be the number of these rounds, the number of epochs, and so on, because it influences the accuracy within the environment. Anyway, as I said, this is still a work in progress, but since the continuum is dynamic, what we are actually proposing is that we need adaptive orchestration in this environment, and that we still need to then deploy and add additional features to the orchestration middleware. And this is also what we did. This is what my PhD student did within this project to extend Kubernetes with additional components so that we can easily deploy such an environment using Kubernetes on a number of nodes. And then we use also the Flower framework, the extended Flower framework for the hierarchical federated learning to run various types of experiments. As I said, the implementation is over, but we need to run still the experiments to show you the actual, performance of the implementation. We are also proposing a kind of reconfiguration decision-making algorithms, because what we have found out is the following: that researchers, do like snapshot analysis of what happens within a certain setup of this hierarchical federated learning, and then of the reconfigured system, but they're not taking into account the cost of reconfiguration itself, because this is something that is happening in real time. When a new node comes into the system, there is a cost of reconfiguration because the new node needs to be joined to either of the clusters, and it does not happen for zero. It brings certain costs into it. So our idea is such that we take into account all this costs in terms of communication and also performance gain, because we need to decide when this new node comes in, it brings with it certain data. The size of the data set, the type of the data also affects where it should connect to. So this is something that we are working on within the hierarchical federated learning pipeline. Yes, so I will tell you also a little bit about our solution for the inference part that we have also recently published and presented at the IEEE Edge conference. It was in July 2024. Here, we also take into account specific QoS requirements to send the data continuously from an IoT device to a service instance which is deployed within the continuum, and take into account also the dynamicity of the system. So certain instances of, for example, for inference can fall out. But what we can also see that some of them can be overloaded. So we are also trying to take into account here the load balancing part, that the services are balanced in a reasonable way. For that, we have implemented also this Q-edge proxy component, which is an addition to Kubernetes, and it's responsible for routing the client request to the adequate service for it to be processed. It is done in a way that we maintain a QoS pool of potential instances that can satisfy defined QoS requirements, such as, for example, latency. And also this load balancing then here comes into play, that none of these services is overloaded. And for this situation, the implementation is also done such that it dynamically reacts to the events happening in the environment. So the events are those that trigger some kind of performance degradation within the edge environment, or you have an update of an instance, a new edge node coming in, and so on. So really this Q-edge proxy is continuously running and monitoring the environment, and then it, based on the changes in the environment, may decide to send a request to another service dynamically. Here you have the details about the implementation, but I would not go into too many details. You can find the implementation actually also online within this software repository of the AIoT project. And here we also did an evaluation for this part of the research on a cluster which was relatively small with 7 nodes, but these are all real nodes being connected through an emulated network. And we were then comparing the performance of our implementation with state-of-the-art solutions. The first one was Kubernetes Node Port Service, and this one is from relevant literature. And actually, we were also dynamically changing the situation within the environment. For example, that at a certain time, you have increased processing time for a certain service on a specific node, where you get degradation of the quality of service, and that you would expect that your network and solution orchestrator reacts to it. Or, for example, here the network latency was increased. These are the events that we can simulate within the environment, and then see how the various types of solutions actually react to it. So the Node Port service, which is built in within Kubernetes, has proved to be inefficient and actually inadequate for this type of dynamic scenarios. For example, here you can see some results, both on a static and a more dynamic scenario, but it does not matter so much to go into details. You can look up the results in the paper if you're interested. But for example, here, let's just explain this right-hand side picture. So it shows that the latency threshold with which you are satisfied with, which is the quality of service is fine if the latency is below 100 milliseconds. So everything which is within here, all requests which are within this bunch of results is okay. But then Node Port was out of this. It could not actually meet the latency requirement most of the time. And then also this proximity, most of the time it could, but then it could not. And for our solution, so the least number of actually requests was over latency threshold for this particular experiment. And also then we looked at the load balancing. So here you can see what was the number of requests that was served by a specific service node. Here you can see that we have approximately the same number of requests being served by 3 components as the potential candidates within this pool, while, for example, the others would, target and overload actually one of the instances. Yes, but for details, please take a look at the paper. Oh, yeah, we have also worked on a completely new topic because not completely new topic, but I think we are among the first to work on this. What happens when you combine federated learning with inference? When the same node is at the same time also doing the learning and inference, which is also possible because in a federated learning set you have an existing model which can be used for inference, and then you can also be learning to change it. And this is recent work also with the Technical University of Vienna, but you can take a look at the paper if you are interested. So let me close my talk. So you have seen, I hope I have convinced you that we have to build edge orchestration tools, especially for AIoT, that deal with the problems with respect to learning pipelines and with respect to inference pipelines. Now we have the basic tools with this, what we have done so far, that we can run many experiments to see what happens actually in a dynamic scenarios or with such solutions. So basically, take a look at our results. I mean, we are now in the middle of the project, so the basic tools are there, and I hope that we will have many new results coming in the following months and until the end of the project. I just have some nice photos from the AIoT team who was working on this, on all this, and during our summer schools. And this is the team here also in Stockholm in April this year for the project meeting. This is in Berlin, also that we were there in 2023. And yes, with that I conclude my talk. And follow us and look at our results and our papers on the web page of the project.
Thank you.